Welcome! In this session, we'll explore an exciting problem, unique Length-3 palindromic subsequences. Together, we'll break down the problem, analyze different approaches, and discuss their complexities. Let's dive in. The problem we're tackling involves finding unique Length-3 palindromic subsequences in a given string S. Now, a palindromic subsequence is a sequence that reads the same forward and backward. Importantly, a subsequence is formed by deleting some or no characters from the string while maintaining the order of the remaining characters. For instance, ABA is a Length-3 palindromic subsequence because it reads the same in both directions. Your task is to determine how many unique Length-3 palindromic subsequences exist in the input string S. The input is a single string consisting only of lowercase English letters, and the output is an integer that represents the count of these unique subsequences. Let's look at the first example to make this clearer. If the input string is S equals APCA, the output is 3. This is because there are 3 unique Length-3 palindromic subsequences, ABA, AAA, and ACA. Each of these subsequences reads the same backward as forward, and no duplicates are counted. This highlights the fact that we're only interested in distinct palindromic subsequences, not repeated ones. In the second example, the input string is S equals ADC. Here, the output is 0 because there are no Length-3 palindromic subsequences. The string doesn't have any repeated characters or a structure that would allow for a sequence of 3 characters to form a palindrome. This demonstrates that not all strings will contain valid subsequences, and the result can be 0. Now, consider the third example where the input string is S equals BABA. The output for this case is 4. The unique Length-3 palindromic subsequences are BBB, BCB, BAB, and ABA. Notice that each of these is distinct, and their characters appear in the same order as in the original string. This example shows how multiple palindromes can coexist within a string, making it essential to carefully count only the unique ones. Let's also consider a few edge cases. First, if the string contains all identical characters, such as S equals AAA, the only unique Length-3 palindromic subsequence is AAA, resulting in an output of 1. On the other hand, if the string has no repeating characters, like S equals ABC, there are no possible Length-3 palindromes, so the output is 0. Finally, for strings like S equals ABABA, where multiple subsequences share the same characters, only the distinct ones are counted. In this case, the unique subsequences are ABA and BAB, giving an output of 2. These edge cases highlight the importance of carefully identifying unique palindromic subsequences based on the problem's constraints. To approach this problem, the most straightforward method is the brute force approach. The intuition here is simple: we generate all possible subsequences of Length-3 from the given string S and check if each one forms a palindrome. To do this, we iterate through all possible triplets of indices I, j, k, where the condition I less than j less than k holds. For each triplet, we extract the subsequence consisting of S, I, S, j, and S, k. To determine if it's a palindrome, we check whether the first and last characters, S, I, and S, k, are the same. If they are, the subsequence is valid, and we add it to a set to ensure uniqueness. While this method is simple to understand and implement, it involves generating all combinations of triplets, which takes n³ time. This makes the brute force approach impractical for strings with larger lengths due to its inefficiency. Now, moving towards optimization, we can solve this problem more efficiently by leveraging some key observations about the structure of palindromic subsequences. A valid Length-3 palindromic subsequence must follow the pattern A_B_A, where the first and last characters are the same, and the middle character can be any valid character. To simplify the problem, we focus on the first and last occurrence of each character in the string. By identifying these positions, we can define a range and count the unique characters in the substring between them. Specifically, our strategy involves 3 steps. First, we create an array to store the first and last occurrence of each character by iterating through the string. Then, for each character, we calculate the range of indices between its first and last occurrence. Finally, we determine the unique characters within this range, which represent potential middle characters. The count of these unique characters is added to our result. This approach reduces the complexity considerably. Since we traverse the string once and count unique characters within each range, the overall complexity becomes O(n squared), which is a significant improvement over the brute force method. An alternative method could involve using a sliding window to dynamically track the first and last occurrence of each character and the unique characters between them. However, this approach is less intuitive and can be more challenging to implement compared to the range-based solution. Ultimately, we select the optimized range-based strategy for its simplicity and efficiency. While the brute force method is easy to understand, its O(n cubed) complexity is infeasible for larger inputs. On the other hand, the sliding window approach, though potentially fast, introduces unnecessary complexity in terms of implementation and maintenance. The chosen optimized approach strikes the right balance, focusing on the first and last occurrence of each character to narrow down the problem's scope. The key insight, or the aha moment, is realizing that we don't need to examine every triplet. Instead, by focusing on the first and last occurrence of each character and analyzing what's in between, we transform the problem into smaller, more manageable subproblems. This realization allows us to achieve an efficient and elegant solution with a reasonable O(n squared) complexity. In this problem, we are tasked with finding all unique palindromic subsequences of length 3 in a given string S. A subsequence is a sequence derived by deleting 0 or more characters from the string without rearranging the order of the remaining characters. For example, in the string ABC, both AC and ABC are valid subsequences. A palindrome, on the other hand, is a sequence that reads the same forward and backward, such as ABA. To solve this, we can start with a brute force approach. The intuition here is simple: generate all possible subsequences of length 3 and then check if each one is a palindrome. This involves iterating through every combination of indices I, j, k, such that I less than j less than k, extracting the characters at those indices, and forming a subsequence. Once we have a subsequence, we check whether its first and last characters are the same to determine if it's a palindrome. If it is, we either increment a counter or store it in a list, depending on the output requirements. Finally, we return the total count of palindromic subsequences or the list of such subsequences. While straightforward, this approach is computationally expensive as it involves testing all possible triplets in the string. To verify if a subsequence of length 3 is a palindrome, we only need to check if the first and last characters are the same. For instance, in a subsequence such as ABA, the condition S I equals S K ensures that it reads the same forward and backward. This simplifies the problem, as the middle character does not affect the symmetry of the subsequence. Once we identify a palindromic subsequence, we either increment a counter or store the subsequence in a list. This process is repeated for all valid triplets, I, j, k, in the string. At the end, we return the total count or the list of palindromes, depending on the problem requirements. Here's a simple pseudocode for the brute force approach. We initialize a counter to 0 and iterate through all possible triplets, I, j, k, or I less than j less than k. For each triplet, we check the palindrome condition S I equals S k. If it holds, we increment the counter or store the subsequence. Finally, we return the counter as the result. While this approach works, it is not efficient for large strings as it involves 3 nested loops, resulting in a time complexity of O(n cubed). There are some key insights that can help us understand the problem better. First, for a subsequence of length 3, we only need to check if the first and last characters are the same to determine if it's a palindrome. This is because the middle character does not affect the symmetry of the sequence. For example, both AXA and BIB are palindromes because their first and last characters match. However, the brute force approach is inefficient. With 3 nested loops, the time complexity is O(n cubed), which quickly becomes impractical as the string length grows. It's also important to consider edge cases. For example, if the string has fewer than 3 characters, no subsequences of length 3 exist. Similarly, if all characters in the string are unique, no palindromes can be formed. On the other hand, strings with repeated characters may contain multiple palindromic subsequences. To implement this approach, we use basic data structures such as a counter to track the number of palindromic subsequences and iterators to traverse the string. Optionally, we can store the palindromic subsequences in a list, though this is generally avoided to save memory. Using iterators like I, j, and k to traverse the string is straightforward, but we can explore optimizations to make the solution more efficient. For example, instead of storing all palindromic subsequences, we can simply count them. This significantly reduces memory usage. Another optimization involves reducing the number of iterations by pre-computing the positions of each character. This way, we avoid redundant checks and improve efficiency. A more advanced optimization involves dynamic programming. By storing results of smaller subproblems, such as whether specific substrings are palindromes, we can build upon these results to find palindromic subsequences more efficiently. For instance, a dynamic programming table can help us avoid recomputing whether certain substrings meet the palindrome condition. These optimizations can help reduce the time complexity of the solution while maintaining accuracy. When analyzing the complexity of the brute force approach, the time complexity is O(n cubed) due to the 3 nested loops iterating through the string. Each loop processes the string length n, so for larger strings, this approach becomes computationally expensive. The space complexity, however, is O(1) if we only count the palindromic subsequences, as no additional memory is required. If we store the subsequences, the space complexity depends on the number of palindromes found. Let's consider an example to illustrate the process. Suppose the input string is s equals ababa. The algorithm iterates through all possible triplets of indices, I, j, k, and checks if the subsequences are palindromic. For instance, the triplet 0, 1, 2 corresponds to the subsequence ABA, which is a palindrome, so the count is increment. Another triplet 0, 1, 3 gives AB, which is not a palindrome. Continuing this process for all triplets, we count all palindromic subsequences in the string. For the input string s equals ababa, the algorithm identifies 4 palindromic subsequences. These include subsequences like ABA formed by indices 0, 1, 2, and 0, 1, 4. The final output is the total count of palindromic subsequences, which in this case is 4. By following the steps outlined in the brute force approach, we systematically generate all subsequences of Length-3, check for the palindrome condition, and arrive at the result. While this method works, it highlights the need for more efficient approaches, especially for longer strings. By leveraging optimizations such as dynamic programming or hashing, we can significantly reduce the time complexity and make the solution scalable for larger inputs. This implementation solves LeetCode problem number 1930, unique Length-3 palindromic subsequences using a center-based approach. The function starts by initializing an empty set to store unique palindromic subsequences. The algorithm iterates over all possible lowercase alphabet letters, 26 in total, treating each as the center of the potential palindrome. For each letter, it identifies the first and last occurrence of the character in the string. If the character appears at least twice, it extracts all unique characters between these two occurrences and forms palindromic subsequences, CXC. These subsequences are stored in the set to ensure uniqueness. Finally, the function returns the size of the set, which represents the total number of unique palindromic subsequences. This approach efficiently handles the problem within the constraints, leveraging string operations and sets to ensure correctness and speed. Here, we begin the Java implementation by importing the necessary utilities. The solution is encapsulated within a class named solution and a method called countPalindromicSubsequence. This method is designed to count unique palindromic subsequences of Length-3 in a given string. To achieve this, we use a hash set called unique palindromes to store these subsequences, ensuring no duplicates are counted. Next, we iterate through all lowercase English letters, treating each letter as a potential center of a palindrome. For each letter, we determine its first and last occurrence in the string using the index of and last index of methods. If the letter appears at least twice, meaning the indices are valid and distinct, we proceed to examine the characters between these two positions. A secondary hash set, scene, is used to collect all unique characters between the first and last occurrences of this center character. Finally, for each character in scene, we construct a palindrome of the form CXC, where C is the center character and X is an intermediate character, and add it to the unique palindrome set. After completing the loop over all potential center characters, we simply return the size of the unique palindrome set, which represents the total number of unique Length-3 palindromic subsequences found in the string. This efficient approach ensures that we only consider valid palindromes and avoids duplicate entries by leveraging the properties of sets. The final solution is both concise and effective, leveraging the power of Java's built-in data structures to solve the problem with clarity and precision. To solve this problem, we start by initializing a set called unique_palindromes to store the unique palindromic subsequences that we find. Then, we iterate over all 26 lowercase letters, treating each one as a potential center character for these subsequences. For each character, we locate its first and last appearance in the input string. If the character appears at least twice, we extract the substring between these two positions and identify the unique characters within it. For example, when the center character is a, its first occurrence is at index 0 and its last at index 4. The substring between these indices is ABC, which contains the unique characters of B and C. Using these, we can form the palindromic subsequences a, B, and a, C, which are added to the unique_palindromes set. Next, we evaluate the center character B. Since B only appears once in the string, its first and last positions are the same, so there are no valid substrings to process. Similarly, for the center character C, its first and last positions are also the same, so we skip it as well. For all other characters from D to Z, they do not appear in the input string at all, which means their first and last positions are both -1, so no processing is needed. At the end of this process, the unique_palindromes set contains 3 elements, a, B, and a, C. Thus, the length of the set is 3, which we return as the result. In this second example, the input string is BABA. As before, we start by initializing an empty set called unique_palindromes. We then consider each character as a potential center. For the center character B, its first occurrence is at index 0 and its last at index 6. The substring between these indices is KABA, which contains the unique characters A and C. Using these, we form the palindromic subsequences B, A, and B, C, and add them to the set. Next, for the center character A, its first occurrence is at index 3 and its last at index 5. The substring between these indices is B, which contains just the unique character B. This allows us to form the palindromic subsequence, a, B, and add it to our set. For the center character C, its first and last positions are both at index 2, meaning it only appears once in the string. Therefore, we skip further processing for C. After evaluating all potential center characters, the unique_palindromes set contains the subsequences B, A, B, C, and A, B. The size of this set is 3, which becomes our final result for this example. In this final example, the input string is ABCD. We begin by initializing the unique_palindromes set as empty. We then examine each character in the string as a potential center. However, since each character in ABCD appears only once, their first and last positions are the same. This means there are no substrings to process, and no palindromic subsequences can be formed. As a result, the unique_palindromes set remains empty, and we return its size, which is 0. To understand the time complexity of this algorithm, let's break it down step by step. First, the outer loop iterates over all 26 lowercase English letters from A to Z. Since this loop always runs 26 times regardless of the input size, it contributes a constant factor of 26, which simplifies to 1 in big O notation. Within each iteration of the loop, we use the find and refind operations to locate the first and last occurrences of the current letter in the string S. These operations each take n time, where n is the length of the string. Because find and refind are called once per outer loop iteration, their combined contribution adds up to 26*n, or simply n overall. This is the first major contributor to the algorithm's time complexity. Now, let's consider the next step, where we process the substring between the first and last occurrences of a letter. If a character appears at least twice, meaning first last, we extract the substring s, first plus 1 last. In the worst case, this substring can be as long as n if the character occurs at the very beginning and end of the string. Extracting the substring and creating a set of unique characters from it both take n time. Since this process is repeated for each of the 26 letters, the total contribution of this step is 26*n, which simplifies to n. Additionally, for every unique character in the set, we add a tuple to the result set. The addition of each tuple takes 1 on average, and since there are at most 26 unique characters, this operation contributes a constant 26 per outer loop iteration. Across all 26 letters, this remains 1 in big O terms. Putting everything together, the dominant factor is the substring processing and find/find operations, leading to an overall time complexity of n. Now, let's analyze the space complexity. The first key data structure is the unique _palindromes set, which stores tuples representing the unique Length-3 palindromic subsequences. Since there are at most 26 center characters and 26 possible unique middle characters, this set can contain a maximum of 676 tuples. This is constant with respect to the input size, so it contributes 1 space. Then, there's the scene set, which temporarily stores the unique characters from the substring s, first plus 1 last. In the worst case, this set can contain all 26 lowercase letters, which is also a constant space requirement of 1. Finally, while the substring s, first plus 1 last, can be as long as n, it is created and discarded within each iteration of the loop. Since we don't hold on to these substrings across iterations, they don't contribute to the overall space complexity. Therefore, the total space complexity of the algorithm remains 1. Let's compare this optimized approach to a brute force solution for the problem. A naive method would involve generating all possible Length-3 subsequences of the string s. Since there are n³ such subsequences, and checking whether each is palindromic takes constant time, the overall time complexity of the brute force approach would be n³. By contrast, the optimized approach avoids generating all subsequences by focusing only on characters that can serve as the center of a palindrome and using efficient string operations like find and find. This reduces the time complexity to n, while using only constant space. Looking at best, average, and worst cases, the algorithm consistently runs in n time. In the best case, where all characters are unique, many steps are skipped. In the average case, the input contains a mix of unique and repeated characters, and substrings of varying lengths are processed. Even in the worst case, where all characters are identical, the time complexity remains linear due to the efficient substring handling. To conclude, the time complexity of the algorithm is n, because each character in the input string is processed a constant number of times. Operations like find, and substring processing are all linear in the length of the string, so the total time required scales proportionally with n. As for space complexity, the only additional memory used is for a few sets and the result container, all of which have a constant maximum size independent of the input length. This leads to an overall space complexity of 1. With this combination of linear time and constant space, the algorithm is highly efficient for solving the problem of finding unique Length-3 palindromic subsequences. To approach this problem effectively, it's important to be aware of some common mistakes that can occur. First, not accounting for edge cases is a frequent issue. For example, if the string length is less than 3, it's impossible to form a subsequence of length 3, and failing to handle this can lead to runtime errors or incorrect outputs. Always check for these cases explicitly. Another mistake is using inefficient methods to generate subsequences. A naive approach might iterate through all possible combinations, resulting in an n³ time complexity. This is unnecessary and can be avoided with a more structured approach. String indexing errors are another pitfall. When working with slices or subsequences, it's easy to mismanage indices, which can cause out-of-bound errors or lead to skipping valid subsequences entirely. Additionally, some confuse subsequences with substrings, assuming that all palindromes must be contiguous. Remember, subsequences don't have to be contiguous, so this misunderstanding can limit your solution. Finally, overlooking case sensitivity or special characters can also cause problems. If you're dealing with non-alphanumeric characters or case-insensitive comparisons, pre-processing the string to normalize the input is crucial to avoid mismatches. When solving this problem in an interview, there are a few key strategies that can set you apart. Pattern recognition is critical. Palindrome problems often rely on symmetry, such as the first and last characters matching. Understanding this can help you prune unnecessary checks and focus only on valid combinations. Optimization is another important aspect. Start with a simple brute force solution to demonstrate your problem-solving process, but then explain how you would optimize it step by step to reduce complexity. Interviewers value this progression. Don't forget to explicitly discuss edge cases, such as empty strings, strings with no valid subsequences, or strings that are repetitive. This shows thoroughness in your approach. For some variations of palindrome problems, dynamic programming can be incredibly effective. If applicable, mention how you might use it to solve the problem efficiently. Lastly, it's helpful to connect this problem to related ones, such as longest palindromic substring, palindromic substrings, longest palindromic subsequence, or palindrome partitioning. By drawing these connections, you demonstrate a broader understanding of the topic. Now, let's explore some alternative approaches and the trade-offs associated with each. One popular method is the two-pointer approach. Instead of generating all possible subsequences, you can use two pointers to check for palindromes directly. This method significantly reduces complexity, but it might require additional logic to handle non-contiguous subsequences, which can make the implementation a bit trickier. Another option is dynamic programming. By building a table to store results for subproblems, like whether a substring is a palindrome, you can solve larger problems efficiently. This approach works exceptionally well for contiguous substrings but may need adjustments to handle non-contiguous subsequences. Finally, there's recursive backtracking, where you generate subsequences recursively and check if they form palindromes. While this approach is intuitive, it tends to be less efficient than iterative solutions and can lead to high time complexity for longer strings. Each of these methods has its advantages and trade-offs, so it's important to choose the one that strikes the right balance between efficiency and code clarity based on the problem's constraints. Great job! We've successfully solved the problem and reviewed key concepts and takeaways. Remember, consistent practice is the key to mastering problem solving. Thank you for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!